Hello and welcome! Currently I experiment quite a lot with various Socket 7 and Super Socket 7 mainboards, and I wanted to have some more different models to play with. So I went through my to-do pile of hardware and decided to repair this cute Gigabyte Super Socket 7 mainboard. To be fully classified as a Super Socket 7 mainboard, it has to support Advanced Graphics Port, short AGP, CPU voltages at least down to 2.2 volts, and frontside bus of 100 MHz. This board does it all and is based on the glorious Aladdin 5 chipset by ALI, which stands for Acer Laboratories Incorporated. The model of this board is GA-5AA and it is manufactured by Gigabyte, as I previously mentioned. This board is a perfect candidate for a very nice retro PC for DOS and early Windows 95-98 gaming. It has 2 ISA slots, 3 PCI slots and 1 AGP. This board was rescued from a scrapyard and has obviously seen some rough treatment. There is a scratch on the chipset, but luckily the fragile brim around the chipset looks intact. Aladdin 5 is a BGA chipset and replacing it would be a huge pain in the back. Such chips are being often damaged by metal hunters when they remove the heat spreader with a screwdriver. But luckily this chip doesn't need additional cooling and so there was no opportunity to damage it. The AGP port has some scratches as well, but those are just on the surface. Some capacitors were ripped off and need to be replaced. Oh, and look at those caps from the CPU voltage regulation circuit, they leaked badly. On the bottom and on the top, electrolyte everywhere. This mainboard comes from the time where so-called capacitors plug was a big problem. The quality of cheaper capacitors was awful. With insufficient cooling and higher clock of the CPUs, they often started puke their content all over the board already after only 2 or 3 years. And this is what we also see on this board. I didn't see such a bad caps plug on PC mainboards since quite a long time. But the good news, as you see from the table on the PCB, the CPU voltage support goes down to 2.0 volts. That's nice, so even K6 2 Plus and K6 3 Plus CPUs can be safely used on this board. Let's continue the inspection. The board is missing the battery holder. Looks like someone just cut or ripped it off the board. No problem, I have replacement holders. It is also obviously missing a BIOS ROM, but that can be obtained from the Retro Web project. I just ran out of EEPROM chips, but I already ordered some. And the board has some bent pins. Let's fix that. I love this tool, it's perfect for straightening the pins. So, looks much better. On the back I don't see any damage. There is a small scratch on the surface, but it doesn't look deep enough to reach the traces. Looks fine to me. One of the memory slots has a broken lever. Well, this is actually optional. The RAM modules would stay in place even with the lever missing. It is just there to push the models out of the slots, so removing the memory modules is easier, though I have to admit that looks ugly. Maybe I can fix that as well. But first we have to check if this board can be revived at all. Yeah, so far I didn't find anything critical. I like the layout of this board and it is almost a perfect Super Socket 7 board. One thing spoils the image a tiny bit. The onboard level 2 cache chip is only 512K. Would be nice to have 1 MB cache, but on the other hand it is such a compact board, there is barely enough space for another cache chip. So I guess it's okay. From the performance point of view, this is not a huge difference. So let's try to get this board working. First of all, there are some missing jumpers which are required to select proper frontside bus clock. There is a table on the board which mentions clocks between 66 and 140 MHz. I doubt that this board would even post with 140 MHz, But today I would like to stay in specs anyway, which are up to 100 MHz, as I previously already mentioned for the SuperSocket 7 mainboard. However, for the initial test, I'll set the jumpers to the lowest possible setting, 66 MHz. Once the board is posting and remains stable, we can test higher clocks. Now the voltage. I would like to start with an Intel Pentium MMX CPU at 166 MHz. That one needs 2.8 volts core voltage. This table is filled with X's and zeros. I'm currently not sure what from that is on or off. Let's assume X is on and 0 is off. XXX0 is 2.8 volts and 000X, the opposite, is 2.7 volts. So even if it's the other way around, the CPU wouldn't be damaged. The accordance switches are 4 through 7. Now the multiplier. As I said, I'd start with 166 MHz MMX and at 66 MHz frontside bus, that would mean multiplier of 2.5. The table on the board says switch 2 and 3 has to be off, if 0 stands for off, and switch 8 has to be on. Now let's check for shorts. Looks good to me, the main voltage rails are not shorted. Let's power it on and check the CPU voltage. Okay, 3.5 volts on this LDO. This must be I/O voltage. Now the CPU core voltage should be 2.8 volts. Look at that, it jumps up and down between 2.2 volts and 2.4 volts. That looks strange. Could be due to a missing load. The CPU is not inserted yet, and switching power supply can go wild when used without a load. Well, let's risk it a bit and add a CPU. I mean, the voltage didn't go over 2.4 volts so far, so it should be fine. Oh, look at that. Now with the load, the voltage broke down to around 1 volt and is again jumping like crazy. Yeah, this CPU is stone cold as well. Well, this means that the core voltage circuit is spoiled, and that is quite obvious if you look at those capacitors once again. I guess time for a recap. I'm not a friend of recapping without a clear suspicion. I mean, it costs time, and so far every time I was stuck and tried to replace capacitors because why not, it never helped. I only change capacitors if they are visibly leaky, bulgy, or the system is unstable due to significant voltage ripple. Otherwise, if a board works fine, I would never touch the caps. However, in this case, I think there is no doubt that these caps are gone. Just look at this. These two caps don't look leaky. They don't belong to the CPU core voltage circuit, so they are not that critical. Most probably they are even okay, but since they were scratched so heavily on the surface, they could be damaged inside, so I'll replace those as well. Let's check some caps, just for fun. This is the one of those scratched capacitors, which is probably okay. It should be 330 microfarad. And it is completely fine, as you see. Even the ESR value is still fine. Just as expected, it looked worse than it is. Anyway, the scratched caps look ugly, and since I have those out of the board anyway, I'll put some new ones. Now the most exciting one, I guess. This is the one which leaked the most. It should be 1000 microfarad one. Let's see what the tester says. 170 microfarad at 6.4 ohm ESR. Wow, that one is really toast. At least it is still detected as a capacitor to my surprise. So here I have some new 1000 microfarad caps, and here are replacement caps for the 330 microfarad. Oh yeah, and of course the battery holder. When soldering the caps, I bent the pins to the side, so the caps remain in place. I also cut off the pins before soldering, otherwise they act as heat spreaders and it is harder to solder the caps. Especially it is worth it when soldering caps on a voltage regulation circuit, where the caps are usually attached to bigger ground and voltage planes, which already diffuse a lot of heat. I often keep the cut off pins, since they are useful for trace repairs, bridges and such stuff. Nice, the caps are replaced, at least all the critical ones. Time to check the CPU core voltage once again. And we have steady 2.7 volts. Nice. Let's insert the CPU and check with load. Also here, 2.7 volts and stable. The voltage is not jumping anymore. On the Retro Web project I downloaded the latest BIOS image and wrote it to an EEPROM. Where I was there, I took a look into the manuals and it turned out that the switches settings on the board are exactly the other way around as I understood those. X is off and 0 is on. So I had to flip all the switches. Everything what was on should be off and the other way around. Okay, let's add a post analyzer card, just in case we will see some codes already. And now, where the switches are set properly, there should be also 2.8 volts on the CPU instead of previous 2.7. And we do have 2.8 volts, that's a good sign. However, there is nothing on the post card. Yeah, the CPU gets warm. And the voltage remains stable. Let's try once again. Nothing. By the way, the speaker remains silent as well. So going through the manual once again, I stumbled upon this power on pins, which is probably to use with the ATX power supply. I used it through an AT adapter, but maybe those power on pins have to be shorted. Let's give it a try. Nope. The system is still dead. You know, let's switch to ATX power supply and try once again. Maybe there is some kind of initialization circuit which is not activated properly. Now I should be able to turn the system on by shorting those two pins. Yay! Look at that! We have some postcodes. That's something, even if I can't explain why there was nothing with the AT power supply. However, we don't see any more codes, neither does the PC speaker beep. It actually should complain about missing RAM. I don't know, let's just add a memory module and see if something will change. Nope. Oh, and look at that, it actually did move on. Wow, it complains about a missing graphics card. That means memory has been detected. Let's add a CPU cooler and a graphics card and hopefully see it awakening. Oh, I can hear memory counting. And there is an image on the display. Look at that. AMI BIOS, Pentium MMX 166, 32 megabytes of RAM. Perfect. Okay, now I'm curious. It works with ATX, but will it work with AT as well? Let's switch it back. And of course it does. Memory is counting and there are postcodes. Wow, this board seems to play completely dead if no memory is inserted. Unbelievable! Cool, now let's add a compact flash to IDE adapter and a CMOS battery to be able to save the BIOS settings. Time and date. Floppy is not connected. The compact flash card is inserted into the first port, so the secondary one can be deactivated for now. Looks like this board supports a lot of different IDE devices out of the box, also zip and LS120 drives. Nice! Okay, let's try to boot into DOS. Seems not to detect the compact flash drive. On the mainboard of this time it should actually. Let's see if BIOS is able to auto-detect the drive. Looks good. Well, let's set it manually and try once again. Nope, doesn't work. I made a cut here, since I tried all kind of different stuff, different memory modules, different settings, and so on, most of which was not really exciting. I was just poking around trying to find a hint. Well, eventually I found the issue. After some trial and error, I decided to try different BIOS images which are available on the RetroWeb project. First one I tried was the beta BIOS F7B, so I thought maybe I should try something non-beta. Accidentally, on the same day, I got a package of EEPROMs which I ordered recently, and I used one of those with the version F6. And suddenly the system started to boot fine. So I thought there is either something with the latest beta version of this board or the EEPROM which I initially used. So I wrote once again the beta BIOS F7B onto one of the new EEPROMs and it just worked. That surprised me a bit, because this EEPROM under the word sticker is the very same SST29EE010 which you can see on the pictures on the RetroWeb. I thought even that I'd be lucky that the last one I have is exactly the one I needed. Well, for some reasons it didn't work. If you compare the datasheets of the SST29EE010 and the Winbond W27C010, they have almost the same pinout and similar specs. However, the Winbond chip needs 12 volts on pin 1 to write, where the SST chip doesn't. It is so-called 5 volts only EEPROM. This Gigabyte board seems not to provide 12 volts on the pin 1, so probably it will not be possible to update the BIOS directly on the board. On the other hand, I don't think this will be a problem, since BIOS updates on this board don't come as often anymore, and if I need to, I can use my chip programmer to write it, so I guess it's fine. I still can't really explain why that SSD chip didn't work. Maybe it was just broken, but the good news is that now the board is booting fine and is absolutely stable. Of course, first thing I tried was Doom benchmark, which ran okay for a Pentium MMX 166. The benchmark finished with 1000 ticks, which is about 75 FPS. Quake benchmark was finished with 44 FPS. I didn't tweak or overclocked anything, just stock Pentium MMX 166 at 66 MHz frontside bus. Speaking of which, it's time to raise the frontside bus clock and try a beefier CPU. I'll replace the Pentium MMX with an AMD K6 2350. I'll leave the multiplier at 2.5 for now and just set the CPU voltage down to 2.2 volts. Let's even go down to 2 volts. Due to the lower multiplier and lower effective clock, the CPU should work fine at 2 volts as well, and we can test the lowest voltage bound too. Now let's set the frontside bus jumpers accordingly to 100 MHz. As I already mentioned, the range is insane. 140 MHz is beyond good and evil, and is probably a good opportunity for some overclocking experiments. But for now, 100 MHz should be enough. So let's give it a go and check the CPU voltage first. 2.0 volts, nice. And on the screen we see already AMD K6 250. That's right, since the multiplier is still at 2.5 from the Pentium MMX 166, that times 100 MHz frontside bus makes 250 MHz. Okay, let's set the multiplier to 3.5 as required for this CPU. All switches to off, that's convenient. Let's put the CPU cooler back and give it another test. AMD K6 350 MHz, nice. And we are getting CMOS checksum errors. I inserted an old battery into the board, which probably is not more powerful enough to keep the settings. I would have to replace that. And the system booted into DOS. Let's try Quake. .8 FPS. That's like 50% faster than with the MMX 166, despite that the AMD CPU has more than double the effective clock and the frontside bus at 100 MHz. That shows once again how much better the FPU in Intel CPUs was compared to AMD. In Doom we are getting 829 ticks. That's about 90 FPS. Once again, those numbers are completely out of the box, without any tweaking at all. And though they give some ideas about the bottleneck which SuperSocket 7 was running against. Raising the clock was not enough anymore. Still, that was and is an exciting, flexible and very compatible platform for DOS retro gaming. That's why it is so beloved in the retro community today. Now, let's get back to the board. As I said in the beginning, one of the main features of a SuperSocket 7 board over a Socket 7 is AGP support. And this is what I would like also to test here. As a test card, this GeForce 4MX should do the job. And we have an image. VGA BIOS seems to be working. Yeah, this card can even do SVGA without additional VESA drivers, and Quake is running with 640 by 480. Well, running is maybe too optimistic, but it makes it at least with 13.5 FPS. Well, Doom runs as well. I will have to do a full test with Windows 95-98 to be sure that AGP is fully working here, but at least so far it seems to be okay. So I would say the mainboard is back to life. At least during some further tests of camera I didn't find any issues. As I said, I'm currently playing a lot with Socket 7 and SuperSocket 7 boards, and I'm happy to have one more board for experiments. Especially as nice as this one. I like it because it is very compact and doesn't take a lot of space on the workbench. But being just compact is not everything, right? There were a lot of similar boards back in the days which were also compact. This board, however, has also a very nice layout. Look how it is split into two parts. All the taller parts are in the upper area of the board, like memory modules and the CPU. Everything is right here in this area. Also a PSU connector, IDE, floppy and I/O ports. Everything is located in the upper part of the board. In the lower part of the board you can find basically only the expansion slots, AGP, 3 PCI and 2 ISA. And since the CPU, memory and all the other stuff is on the top, the area behind those expansion slots is totally free. So you can use long cards, like for example a pair of 3DFX Voodoo 2 cards, which are at least as long as this mainboard. Also that you can use one row of switches for almost everything is great. Only for frontside bus you would have to reset the jumpers, but multiply and voltage are completely set in one place. The only thing is that the switches are located behind the expansion slots, what would mean that you would have to remove long PCI cards to get to the switches. Talking of switches, it's nice that the voltage on this board can be set up down to 2 volts, so even AMD K6 2+ and 3+ can be used here without over voltage. With the new capacitors the voltage is also very stable and this board should serve well another decade or so. I'm also glad that I replaced those scratched capacitors. Even if they were technically okay, it just looks nicer to have new caps. Speaking of nicer, there is one more thing I would like to fix: the broken memory slot lever. As I said, it's not really necessary, but having a proper lever would make it easier to get the memory modules out of the slots. Here I have one from my spare parts, but it looks different. It probably will not fit. I have to look through my scrap if I can find something else. Well, here's another AT board, which seems to have the same slots. I guess I can take one lever from here. I showed this board in one of my previous videos. It is a slot 1 i440BX board, which is also quite nice, but the chipset was unfortunately damaged and replacing that is, to be honest, yet beyond my skills and capabilities of my hobby workshop. Anyway, such broken boards are still very useful since they provide a lot of replacement parts, like the lever which we need today. Perfect! Looks even better than the other scratch ones. Maybe I should swap all of those later. Let's test. Cool! The module is even jumping out of the slot. Here another 32 MB of RAM. I'd say 64 MB is what a K6 II should have at least. Today we can find plenty of SD RAM modules, so that is luckily not a problem. So, and this is it for today. This board is working again, the CPU voltage is stable, it got new caps, latest BIOS, and even the memory module lever has been fixed. I'm very glad to have this board now in my workshop for experiments, and I hope I could bring you some joy with this video too. Thank you for watching and goodbye.